All right. Can everybody see that? See my screen?
Yes.
All right. This just still visible when I put my laptop tablet on. That's still visible, yes?
Yeah.
All right, great. So we got about a minute. And while we're waiting, does anybody have any questions about anything so far? So the plan is on Friday. Once we finish this section, the plan is on Friday to work through that workday handout with all the different questions on it. That's what we'll do Friday, and then we're gonna move on from this section because you already had stereochemistry in part one, so I don't want to beat a dead horse. I did want to introduce a little bit more in-depth topics, so that's why we've been talking about how it applies in different settings like medicine and with medicinal compounds and synthesis. And today we're going to push that a little bit further and talk about how to induce chirality, because we talked about the other day the big molecule we were looking at in class, enigmazole B. We talked about that and talked about how all those stereocenters had to be set a certain way. They all had to have a certain configuration because there were, what was the total? 256 possible stereoisomers of that.
Yep.
So that was that one that we showed was the one that actually had the anti-cancer properties. And more than likely, the original compound was extracted from some natural source, maybe a plant or a sea sponge or something like that. A lot of those alkaloids like that, they get them from different types of sea sponges, coral, but you don't want to destroy like a coral reef to get a milligram of compound. So that's why you have to be able to synthesize those compounds in a lab and scale them up so you can make a lot of it. Let me see. Oh, we're already recording. Great. All right, so we're just gonna jump in. It's 9:06. And for those who just came in, I'm gonna put the notes in the chat one more time before I get started. Uh, and then we'll roll. Right, because the first part that we're going to talk about, this catalysis part, um, that's not on the handout, but I want to show you like what it is and how it works so that you'll have knowledge of it. So today we're going to talk about inducing chirality, and there are two ways to do that. Morning. There are two ways to do that. One way is through catalysis. All right, that's one way. And we're going to talk about that for a brief moment. And then the other way is to use molecules that already have stereocenters present. So that's what the handout is talking about, those pre-existing stereocenters. If you watch the video, also you saw some of this, right? I talked about the catalysis and how certain types of catalysts are used when you want to do a reaction and do it with what's called stereo specificity, right? You want to create a stereo center or a chiral center. There, there are many tools to do that. As a matter of fact, I was just looking up a paper. One of the Nobel Prize winners was a chemist by the name of David McMillan. I think he's at Harvard. I can't remember what school he where the school where he teaches, but he won a Nobel Prize for asymmetric catalysis. Only he didn't use metals. He used organocatalysts. So we're gonna talk about that. So I found this paper because I wanted to be able to illustrate this, and this is in the chat. If you want to grab that handout from the chat and download it real quick, do so. But I found this paper just to illustrate the point. So this reaction is and we're going to talk about this later. It's an aromatic reaction. It's a Friedel-Crafts, what's called a Friedel-Crafts alkylation. You don't have to worry about that part yet because that's a later. We're going to talk about Friedel-Crafts and aromatic compounds much later. But that's what the reaction is. And if you notice, you're taking an aromatic compound, indole, which is, come on, indole, which is this compound right here. Right, and you're adding it. Sorry about the mess. You're adding to it, right, this nitroalkene. Right. What I want to point out is the product. So in the product, I want to introduce you to a couple of other topics as well. But in the product right here, right, notice that now you've set a chiral center here. Right, that's a chiral center. And the chirality is defined here, right? It says 81% EE. You've never seen this EE before, so I'm going to introduce it to you now. The percent EE is what's known as the enantiomeric excess. I'll write that down.
Come here.
Some reason. Let's write it underneath. Right, enantiomeric excess. So that's basically a ratio of the enantiomers. So in this case, if it's 81% EE, that would be a let me see, roughly like a 90 to 10 or a 90 to 10 ratio, right, of enantiomer. So you'll have 90% of, let's say, R and then 10% of S, right, roughly. So when you see that term enantiomeric excess, that is a ratio of enantiomers. All right. So you got a chiral center that's set. You got roughly 90% of one enantiomer, which is actually not too bad. And 10% of the enantiomer that you don't want, which is actually, again, that's not too bad. The only thing is you can't separate them. Enantiomers you cannot separate. Diastereomers you can. But the point is, I took this indole, I added this nitroalkene to it, and I set a chiral center, and I made a molecule that actually has some type of biological significance. Like this molecule is actually a precursor to a larger molecule in a convergent synthesis. But the way I did it, or the way that they did it, is through a process called asymmetric catalysis. Asymmetric catalysis, right? This is typically done with a transition metal and what's called a ligand. So over on this side, you can see here that you have a copper. That's your transition metal. And then you have this isoxazoline type,
Like absolute fucking divine authority over everything.
right? And that is what's going to bind to copper, right? So you have ligand. Can you mute, please?
You said, fuck you, sir. Probably.
Somebody needs to mute. So you have your ligand, which is here, and then your metal. And those two things are what's required to do asymmetric catalysis. Well, not just any ligand. It has to be a chiral ligand. Right? And you can see right here on the ligand, the two substituents here are opposite or chiral. So this particular type of ligand, we call it C2 symmetric. So it's a C2 symmetric ligand. So you need a chiral ligand, you need a metal, and then that actually forms what we have here. You can see where the ligand is bound to the metal, right? This is called a complex. So it's that complex that actually catalyzes the reaction, and it causes a bias so that one enantiomer or one stereoisomer is favored over the other. So let's write that down. So the metal ligand complex right, it catalyzes the reaction. Number one. What's a catalyst, by the way? Anybody? What does a catalyst do if you add a catalyst to a reaction?
It speeds up the
It
reaction.
speeds it up.
Increases the rate. That's exactly right. It increases the rate by lowering the activation energy. So this catalyst increases the rate of reaction, but it also causes a bias in that step where the chirality is set, right? So that's the purpose of using a metal ligand complex like this. So one way again to create chiral centers is to do what? To do asymmetric catalysis, where you take a metal ligand and you complex them, and then you use that as the catalyst for your reaction. So let me show you quickly before we move on to the next. Well, first of all, any questions about this before I show you like how this actually works? Right. So for this to happen, you need a metal, you need a ligand. It doesn't, a lot of times the reaction is going to be based on like your needs. What are you trying to do? What are you trying to synthesize? What stereo chemistry you're looking for, whether you want to set multiple stereocenters or just one. All of those things are factored into like what metal and what ligand you use for what specific reaction. Like a lot of times your catalyst is specific to a certain type of reaction. All right. So let me show you the cycle. I know this is a lot. That's why I put the notes in the chat, but I'll show you the cycle. So first here, all right, that's your complexation step. Typically, you just take it, stir it in a solvent, stir the metal and ligand together. And then notice in the next step, you add in your starting material, right? And that binds to your metal ligand complex. That's what this structure is here, right? So the starting material binds to the metal ligand complex. And then notice, let me zoom in on that. I want you to notice something here, right? If you notice the stereochemistry of your two substituents, again, we point that out. Which way is that going if it's on a dash line? Is it going into the screen or coming out of the screen?
Into the screen.
It's going back, right? That doesn't change. It's going backwards into the screen. And then by default, what about the other substituent? Notice that's on a wedge, right? So which way is that substituent pointed? Is that coming out or going back?
Dr. Russell, did he ask me?
Anybody? You can
Anybody?
answer it. Yeah, go ahead.
And you said which substituent?
Yeah, we're looking at the one that I have highlighted in purple right here.
Oh,
I can't join
that
online
one is
classes
pointing
if she
outward.
don't work.
I'm sorry, what did the other student say?
I don't know. Y'all were talking at the same time. So you go
Okay.
first, and then whoever that was chiming in, you can come after that. Go ahead.
Well, the one that is like connected to the end and then goes out to like the skinnier line, that one's pointing outwards, and then the one that has the dash line, that one's pointing inwards.
Okay, so one is pointed back into the screen and one is coming out of the screen. So this is the one that will be out. Is that right? And that substituent on that side will be pointed back. But the point is, because those substituents are situated how they are, they're going to create a bias. So when the reaction happens, right, one of those stereoisomers is going to be favored over the other. So that's when it's talking about here, right, where it says that one of the faces, because this is where the reaction is taking place on the double bond, right here. So one of those faces is blocked and the other face is more accessible based on how that ligand is set up. And that's how you create or generate your chirality, right? This is the step where the stereochemistry is set right here. So in one case, the double bond, the one side of that double bond is blocked, and in the other case, the other side of the double bond is open, right? And because of that, that's why you have this bias. That's why you have a bias. Sorry about that. I just saw a spider coming down on my window. My bad. But once that's where the bias comes from. The fact that you create this pocket around the metal and whatever's attacking that alkene can only attack from one side or the other. Right. So that's where the bias comes from. That's where the the ratio comes from, where one enantiomer is favored over the other. But all of that to say that when you do asymmetric catalysis, what you're doing is you create a bias, which is necessary in order to favor one stereoisomer over the other. And I'm gonna write that down. Questions about this part? Right. So one of those substituents is blocking one face, the other face is open, and because of that, you get one stereoisomer favored over the other. So let me put that here, right? So the catalyst, what does that ligand around the catalyst do again? How do you get one stereoisomer favored over the other? What was the term I just used? Right, the catalyst creates a bias, right? And because of that bias, one stereoisomer is going to be favored over the other. Right? So because of that bias, you favor one stereoisomer over the other. And what you get as a result of that is an unequal mixture of stereoisomers. All right. That's the main point. When you do asymmetric catalysis, it creates a situation where you get an unequal mixture of stereoisomers. That's the goal, right? You want one isomer to be favored over the other. So this is one way to do that, right? Take a metal, take a chiral ligand, use that as your catalyst, and then whatever reaction you're doing, the outcome is going to be an unequal mixture of stereoisomers. And we saw that in the information up here, where we said we have 90% of one and 10% of the other. All right. Any questions about this part? All right. Let's go to the second part of our discussion here. This is the part that was I think there was some information in the video about asymmetric catalysis too, though. It just wasn't as detailed, I don't think, but more visual. All right. So let's think about this in terms of what was the second way we said we could induce chirality? One way is to do asymmetric catalysis. What was the second way we said? Anybody? So one way is to use catalysis. Second way, to use a molecule that already has a stereocenter built in. So a pre-existing stereocenter. Let me ask this question. If you watch the video, what is when we talk about bias and pre-existing stereocenters, what are we talking about when we say, somebody tell me, finish this for me. So if I take something achiral plus something chiral, what would that give me in terms of stereoisomers?
Oh, it's the pre-existing stereoisomer, but in our notes it said that it comes out as non-race mixture.
Okay, good. So it will come out as non-racemic. That's excellent. Or another way to say that is then unequal mixture. Now it's not just a mixture of anything, it's an unequal mixture of stereoisomers. Right? What does racemic mean? Anybody catch that from the video? What does that mean? That term. That's typically if you take two achiral things and put them together. So something that's achiral plus something that's achiral. So two things, no chirality whatsoever. You're going to get what's called a racemic mixture. What does that term mean? Racemic. Anybody?
It means
It's
equal
like
mixture of R and S.
Equal mixture of R and S. That's exactly right. 50-50 of each stereoisomer. So no bias, no inequality. You get equal amounts of both R and S. Right? That was definitely in the video if you watched it. Thank you for that. So you get a racemic mixture if you take two achiral things and put them together. If you take something chiral plus something achiral, you're going to get a non-racemic mixture. And what that means is that you're going to get more of one stereoisomer than the other. All right. Thank you, Chloe. I think I just saw that. I didn't know that was something in the chat. Appreciate that. All right. So let's go. Let's apply this. Right. Again, we talked about chiral catalysts. That's one way to make chiral centers. The other way to make chiral centers is to start with a pre-existing chiral center and use that to dictate the stereochemistry of a reaction, right? And again, let's take this back to the essence. Why is this important? It's important because when you make products that have or compounds that have medicinal properties, when you make compounds that have biological properties, a lot of times those compounds need to be chiral in order to fit into the receptor in a cell, a specific receptor or something like that. So that's why the chirality part is important. And then the other part is, how do I make these compounds so that they're chiral, so that they contain stereocenters? And the answer to that is to use a catalyst, a chiral catalyst, or to use a molecule that already has a stereocenter present so it can dictate the chirality. So let's look at the reaction. If you got an A or a B in part one, you should be able to tell me what this reaction is, like what the outcome is. Now, you already have the product, so that that part of the battle is already over. So hydroboration oxidation does what? Anybody? I'll buy you lunch if you could tell me what that reaction does without looking it up. It's different being on Zoom because you can actually Google that.
I
But
was
tell me what
definitely
that
gonna
reaction
Google
does.
that.
I know somebody was Googling it trying to get that Chipotle or whatever, Fuddruckers or whatever. But
Ooh, not
sorry.
Fuddruckers.
All right. What does that mean? Hydroboration/oxidation. What type of reaction is it and what does it do? This is your part one review for today. Anybody?
You said oxidation. What else?
Can you see the screen?
No, it just went away. I don't know.
Oh, so the screen is not visible?
Well, I'm on my phone, so that's probably why.
Okay.
I saw it for a second and then
Hold up. Let me do a new share. Okay, Kaylee. Thank you for that. You get another free lunch pass. It turns alkenes into alcohols. I don't know, but that's fine. I see it in the chat. It turns alkenes into alcohols. Excellent. That's so true. That's what we learned that in part one. All right. It also has compared to the another reaction that is grouped with to turn alkenes and alcohols, it has a specific regiochemistry. How many of you remember this term? We're going to see if you, let me see if you can jog your memory. Anti-carbonyl. Anybody remember that term for part one? Got to get back in the classroom. I hope they finish this project today. Anti-Markovnikov means what? I see something in the chat. Oh, that's something else. All right. All right, we'll come back to that. That's part one. And that we'll come back to that. All right. I need you to be able to tell me that on Friday, though, what that term means, anti-Markovnikov. Because really, that's the key to both of these problems, understanding that. As a matter of fact, can somebody look that up? We need that today because that's the key to understanding these problems.
What is it again?
it said that it bonds to carbons that have less substituents as opposed to
Right,
more.
right. So anti-Markovnikov means for this reaction is that the alcohol, which you can see in the product, adds to the least substituted carbon. Right? It adds to the least substituted carbon. What do I mean by that? Right? Let's look at it. This is my alkene that I'm adding to right here. Which carbon has the most carbons attached to it in the double bond? Let me zoom in. You can see the double bond, right? You got a carbon here and a carbon here. Which carbon is more substituted in that double bond based on what you see? Which one has the most substituents attached to it? You only have two choices. It's either the one on the left or the one on the right. Which one?
Left.
On the left? Yes. That's the most substituted carbon in that alkene. The one on the left is the least substituted. The one on the right is the most substituted. All right, so this is least, and then this one here is the most substituted. Right? It has more bonds to carbon. That's all that means. One side has more bonds to carbon than the other. All right. And this is the stereocenter that's already in existence. This is my pre-existing stereocenter here on this carbon. All right. All this stuff is necessary to understand like what the question is asking. Right. So let's get to that part. Any questions about least substituted, most substituted, anything before we move forward? All right. So let's look at the question. Can somebody unmute and read that?
Hydroboration, oxidation of our
Yeah, just skip that.
trimethyl.
You can skip that part.
Okay. So part A. Which product we expect to be formed in the highest amount? What is the relationship between the two products? And explain why the products are formed as an unequal mixture of stereoisomers.
All right, great. Let's do the last part, part C first. Why do we get an unequal mixture of stereoisomers? How do we create that scenario? If I want an unequal mixture of stereoisomers, what do I need to react together?
Chiral
And I'm not something that's good, something that's chiral, and then something that's what? Achiral. Do I have a chiral starting material? One of them, right? Is the alkene, is that molecule chiral? Does it have a chiral center in it? Right. This is my starting material, my alkene that I have highlighted. Is that oxygen, that carbon where that oxygen is that a chiral center?
Yes.
Why y'all act scared to say yes? We've been doing chiral center. You know, what are the criteria? 4 different substituents, sp3 hybridized. What else? Non-symmetrical. And what's the last one? Go ahead.
Super non-superimposed.
Non-superimposable. What?
Mirror imaging.
Mirror image. Right? As a matter of fact, let's go ahead and figure out what the configuration of that center is. Which one of those? So the chiral center, I'm gonna change colors on that. The chiral center is here on this carbon. Everybody agree with that?
Yes.
What's
Yes.
missing? What's not shown?
The
The
hydrogen
hydrogen
Which direction is it gonna be pointed?
On a wedge.
towards us.
On the wedge. Good. So it's right here. Right. So oxygen we know is highest priority because it's compared to the other two atoms, which are both carbon. Which carbon is going to be this one and this one here? Which one of those two carbons is going to be 2? We know hydrogen is 4. Is that right?
The double bond carbon.
The one in the double bond. Good. So that's 2, and then that makes that 3 over here. What is that? Is that counterclockwise?
yes.
But what?
The hydrogen is on the wedge, so you make it R configuration.
So it's R. Good. Excellent. All right. So we know that we have a pre-existing chiral center. It's already in place. And when we do the reaction, that chiral center is going to dictate the outcome of the reaction. It's going to dictate by creating a bias. We talked about that a second ago. It's going to determine which one of your two products are formed in the highest amount. So why is there we're looking at C now. Why is there an unequal mixture? because we took something chiral and reacted it with something achiral. That's one of the two ways to get an unequal mixture of stereoisomers. Take something chiral and react it with something achiral, or use a chiral catalyst, which we've already talked about. And that's not the case here. All right. Everybody okay with that? So the explanation for why the two products are formed in an unequal mixture of stereoisomers is that one of my starting materials is already chiral. So chiral plus achiral is going to give you an unequal mixture of stereoisomers. Is that right?
Would you mind repeating that?
Yeah. So the question asks us to explain why the products are formed as an unequal mixture of stereoisomers. And we said up here, the way to generate an unequal mixture of stereoisomers is by taking something chiral plus something achiral, right? So that's why when we looked at that star material and looked at the chiral center that's adjacent to the alkene, that chiral center makes the whole molecule chiral. So that's my chiral thing. And then the achiral part would just be the BH3, right? Added to that double bond. So something chiral plus something achiral will always give you an unequal mixture of stereoisomers. All right, we're good on that part? All right, let's look at B. We're working backwards. What's the relationship between the two isomers, or the two stereoisomers? In other words, are they mirror images, or are they diastereomers? Are they identical? What do you think? Just unmute and chime in.
Are they diastereomers?
They are. Tell me why you say that. You're right.
Well,
You're
they're not
100%
mirror
correct.
okay. They're not
Go
mirror
ahead.
images because they're like it's basically the same molecule, but the alcohol at the top, and the first one is on the wedge and on the second one it's on the dash. And I remember last class when we did diastereomers, it was the same molecule, but they were just kind of those were placed differently. So yeah.
Okay. So what would the mirror image of, let's say, let me scroll up so I can see if it's later. Yeah, what would the mirror image of A look like? I see Kaylee. Thank you. I see it in the chat. Good. Only one of the chiral centers is changed, not both. What would the mirror image look like?
Both of
Of
the
A.
chiral centers will be changed.
So the mirror image of A would look like this, wouldn't it? I'm going to abbreviate it. So this would be on a wedge. That would be on a dash. O S I'm just going to say R3. Is that right? Why this pen is sticking? I should have used a stylus. Yep. That's what the mirror image would look like. Well, both stereocenters are different. But in B, that's not the case. Only one of them is different, just the alcohol. The pre-existing chiral center didn't change. So they are diastereomers, right? Any questions about that part? Right? Diastereomers are stereoisomers, but they're not mirror images. But they're still stereoisomers. How do we, and just to jog your memory, even though we've already heard it, what's the difference from the original image and a diastereomer? How many stereocenters are we changing?
Only one.
Only one. Good. If I had 10 stereocenters, I would change one at a, if I changed one at a time, that each one of those changes would give me a diastereomer. If I changed them all at the same time, it would give me the mirror image. All right. Are we okay so far? All right. Let's look at question A. Which product would you expect to be formed in the highest amount? Right. Obviously, the ratio is given. A is formed in 80%, and the other, the diastereomer B is formed in 20%. But the question now is why? Why do we see this unequal mixture? What is it about that pre-existing chiral center that causes that bias? What do you think? Look at the alcohols and how they're oriented relative to the pre-existing chiral center and tell me what your thoughts are on that, especially if you watch the video. Anybody but a dead body. All right, why do you think that is? That one of those isomers is formed in 80% and the other in 20, and the configuration is what it is.
Is A more stable than B?
Yes, it is. It is. Tell me why you say that. Why did you refer to the stability of A over B? You're right. It is more stable, and there's a reason for that we can discuss now. But I want to know why you said that. That's a good observation.
You got me there, Dr. Russell. I honestly don't know.
Okay, but so you made the statement that A is more stable than B. That's true. There's a reason for that. So let's talk about it. Let's look at A and let's compare it to B, right? This is the stereocenter that already existed. Now, in A, the hydroxyl group relative to that stereocenter, where is it? Is it on the opposite side or on the same side? Right? We should know this. We know what a dashed line means, and we know what a wedge line means. Am I right? In class, y'all was shushing me. We already know what dash mean. Now, it's like you can hear a rat pee on cotton. Which, are they on the same side or are they on opposite sides?
Opposite sides.
On opposite sides. One is going back into the page. That's your chiral center that already existed. And the other, the OH, is coming out of the page. Is that right?
Yes, sir.
Mm-hmm. What about B?
They're both on the same side.
Same side, right? So the fact that A, the substituents, I see a bunch of stuff in the chat. Opposite, let's see, same. All right. B is on the same side. Yes. A, the substituents on opposite sides. Yes. Thank you for putting that in the chat also. But how does that affect the stability? Right? There's a term, you probably learned this in part 1. Term called steric hindrance. Anybody remember that term from part 1? Or the term sterics, period? I recall that term from part 1.
Is it like when the groups are close together, it causes more strain?
Yes. Yes. Say that again.
When the groups are close together, it causes more strain on the...
That's exactly right. And what does strain do in a molecule? Does it make it higher in energy or lower in energy?
Higher in energy?
If you add strain, you increase the energy. That's exactly right. And so when you look at A, because these two groups are on opposite sides, that lessens the strain or the steric hindrance in A, right? So the groups that are, let me not do that. So the groups in A are opposite. So less strain means more stability. So you're right, 100% correct in saying that A is more stable than B. But the reason is because of how the groups are oriented. The fact that those groups are on opposite sides of one another. That's why A is more stable than B. And that's why you get more of it. If you look at the ratio, scroll back down. If you look at the ratio of A to B, I can scroll down. Come on, word. Right? Notice A is formed in 80%, and then B is formed in 20%. Right? Why do you think B is formed in a smaller amount?
It's less stable, so it's harder to form that product.
Yes. B is less stable. It's harder to form that product because the amount of energy it takes to get to it is higher, right? So basically what this is in reality is like it's a mixture, right, of kinetics and thermodynamics. Kinetics just deals with the rate of reaction, and then the thermodynamics deals with the stability of your product. So the way to think about this without going into too much intricate detail, we start at the alkene, and then we basically have two pathways we can follow, right? So this is going to be the pathway to A, and this is going to be the pathway to B, right? Y'all recall this from part one? Energy diagram, anybody? What's on the x-axis? Anybody? Time. Y-axis is what? Energy. Is that right? And then what is the gap between where the starting material is and the top right here?
Is it activation energy?
Activation. Excellent. Put your, who is that?
Bobby?
Bobby. Put your Zelle in the chat too. I'm gonna have to buy 2 people lunch today. That's exactly right. What is that? What is the activation energy control? What does it control? Anybody. If you're doing a reaction,
It's the amount of, like, the minimum amount of energy needed to start the reaction.
yes. So it controls the rate, doesn't it?
Yes.
It controls the rate, how fast the reaction goes, how rapidly the molecules that are reacting collide with one another. It controls all that, right? So you notice B has a higher activation energy, and B is also, the product itself is higher in energy than A. So that's where that unequal mixture comes from. Not only does it cost more energy to get to B, B is not as stable as a product either because of that steric hindrance. So that's why you see that 80-20 ratio of A to B, because B is harder to access and is less stable due to steric hindrance. Right. So that's why you see that when they ask about the unequal mixture, that's the underlying reason behind why there's an unequal mixture. The obvious reason is because there's a chiral center present already. The underlying reason is that one of those products is harder to access than the other. So that's why you don't get as much of it. All right, we're going to stop right here. Any questions about anything? All right.
I do have one question.
Go ahead.
You know how they're doing the chemistry lab for tomorrow?
Say that again.
Do you know about how they're doing the chemistry lab for tomorrow? I know my other classes, they moved to
And you
bio.
mean, yeah, and your classes in Armstrong?
Yes.
Yeah, so the labs tomorrow are not going to meet. All the classes in Armstrong won't start back meeting in person until Monday. That's the plan.
Oh wow. Okay.
Yeah, only in
Okay.
Armstrong now. Nothing else is virtual. Just the classes in Armstrong. So don't don't look for Zoom links for a class that's in Kenny already or in another building, or don't not show up and then say, "Oh, I thought it was," because when I saw the Canvas message, I edited mine because all the teachers we had the same message that the classes would go virtual until the 30th. However, it's not all classes on campus. It's only the classes at Armstrong. So make sure you know, take note of that because everybody else is rolling as regularly scheduled. And then Monday we're out, right, for Labor Day. Is that right?
Yes.
Yeah. So hopefully they'll be done with what they need to finish on the roof, or at least get to a stopping point, and then we'll be back on track on Wednesday because we're out Monday.
Okay.
All right. Kaylee, did you just type the question? The products form unequal stereoisomers because yes, that is absolutely correct. The products of a reaction where you have one of your starting materials being chiral, that chiral center is going to dictate the outcome. It's going to cause the products to be achiral. I'm sorry, it's going to cause the products to be chiral, but to be in an unequal mixture. So yes, the answer to your question in the chat is yes.